This is the second lesson that we're going to have a look at finding the areas for polar curves. What's going to be slightly different about this lesson from the last one is that rather than just finding the area enclosed by one curve, we're going to look at finding the area enclosed between two curves. Now, you've already done some of this with your standard integration with curves, but you approach it in a slightly different way with polar curves. If you think about how you define the arguments for the integration, we're going to have to think carefully about what values we're going to use for our limits for our integration, which values we'll use for which curves. Okay, so quick reminder of the formula. So this is the formula that we use. It's in the formula book. So remember the half. It's a half integral r squared d theta. And if you remember where that came from, it's because it's the area of a sector, which is your half r squared theta. Now, what we've got to think carefully for this, and quite often the questions will get you to maybe draw a diagram first, which you can use to help you. If they don't, then you certainly should do that. So we can use that formula to find areas between curves by choosing which of the curves we're going to integrate between which limits. Okay, so probably the best way to do this really is to have a look at a couple of examples. Okay, so here's our first example. So if you want to just pause this for a minute and then write it down. So you can see the first part of the question says, on the same diagram, sketch those curves. You should be quite familiar really with what those sorts of curves look like. So if we look at them one at a time, the first one we'll look at is r is 2 plus cos theta. Now what's useful when you're sketching is to think about tangents to the pole. Okay, so remember your tangents to the pole, okay, are when r is 0. Now if we think carefully about this one, okay, when r is 0, that would give cos theta equals -2, which we know doesn't happen. So there are no tangents to the pole for this one. So basically the curve doesn't go through the pole. Okay. The other thing we can think about is maybe what value theta is 0 gives us. If we give theta is 0 in there, we should know that cos of 0 is 1, so we'll get 3. So that gives us an idea that the curve is going to intersect on the initial line at r equals 3. Okay, so let's have a look at the second one, r equals 5 cos theta. Now we know with ones like this that if they've just got a single cos or a single sine, then that's going to be circles. So again, useful thing to do is think about tangents to the pole. Okay, so for this, r is 0. So what we get for that is cos theta equals 0. So our tangents to the pole are going to be theta equals plus or minus pi by 2. Okay, so that gives us an idea of how the circle behaves as it goes into the pole. Other thing, let's just have a think. If theta is 0, what do we get for r? We get r is 5. So I think that should give you quite a good clue as to what those look like. Okay, so you have a quick sketch of those. I'll show you what your sketch should look like. Okay, here we go. So r equals 5 cos theta, that's our circle. We know it goes on the initial line at 5, so this has the value 5 here. Okay, and then goes through, there's my tangents to the pole. Can you see the vertical axis there? The other one, it's not quite a circle, it's one of these limosons with a flat side to it. Okay, we know that when theta is 0, r is 3. So what's useful with that is that you can sort of place that just inside the other one there. Okay, so there would be marks for this in the exam, so do please make sure that your sketches are reasonable sketches. Okay, now the question is leading us through this nicely. It says find the polar coordinates of the points of intersection. If it doesn't ask you those, when we're going to look at the region, the shaded region, we would need to find those points of intersection, because those points of intersection are what give us the boundaries for the limits between the two different curves. Okay, so just remember, if they don't ask you to find them, then that is something that you would need to find. Okay, where do they intersect? Well, let's put them equal to each other where the r's are the same. So 2 cos theta is equal to 5 cos theta. Okay, so from that you can see we get 4 cos theta equals 2, or we get cos theta equals a half. Okay, pop that in your calculator and we get theta equals plus or minus pi by 3. Now don't get really excited and move on, because can you see what the question is asking us for? Polar coordinates of the points of intersection. Do you remember polar coordinates? They look like r theta. So for these values of theta, we're going to have to work out what r is. So let's do that then. If theta is pi by 3, remember, because it's points of intersection, we can sub it in back into either of those. So I might put it into the 5 cos theta one. Okay, so 5 cos pi by 3 gives you 5 over 2. Okay, and you can sub this one back in if you want, but you should also know that cos of minus theta is the same as cos of theta, so you also get 5 over 2. Okay, question, remember, asked you as polar coordinates, so if you don't state them as polar coordinates like this, why have I written that? If you don't state them as r theta, then they'll take some marks off you. So that's my first one, and that's my second one. Okay, so that's my answers for those. All right, so we now know what these points of intersections are here, and we're going to use those in a minute to find the area of the region which lies between the curves. Okay, so that's part A and B done. I'm going to need a little bit more room for part C, so I'm going to just take us on to the next slide. Now, here's the bit that we need to be quite careful about. We know where the points of intersection are, but we also know when we integrate polar curves, we are looking, our limits are always straight lines that come out from the origin, so they're values of theta. So I've drawn a line out from the pole that goes through my point of intersection, and we know that that is theta equals pi by 3, because that's what we just worked out in our first part of the question. So we've got 2 bits of area that we need to find. The first bit is that shaded part there. So what we need to think about is which curve encloses that shaded bit. Let's call it A. Which curve encloses A, and between which limits or which values of theta. Now you should hopefully see that the curve that's the boundary for that region A is my r equals 2 plus cos theta curve. Okay, and the limits that we'll need to use to get that area A, well, it starts with this line here, which is theta is 0. And it goes up to that point of intersection, which is theta is pi by 3. So I think this is the thing that's a little bit different from where you're integrating normal curves, because you're always looking for those horizontal and vertical lines for your limits. Okay, polar curves are different. Remember, your limits are coming out from the pole, and they are values of theta. Okay, so the second bit we need to do, I'll just put some lines on there, and I'll call that region B. Okay, now we can see region B. Look at where the boundary of it is. The boundary is the curve r equals 5 cos theta. What are we going to use for our limits? Well, we can see again, the lower the limit is the point of intersection. So that's theta is pi by 3. And my upper limit, can you see my upper limit here, is my tangent to the pole. Okay, so it's between theta is pi by 3 and theta is pi by 2. That is the trickiest bit done. Okay, the rest of it is purely just applying your formulae. All right, I'm going to use the symmetry of both of these curves. Okay, so when I do my area formula, remember my area formula is half integral r squared d theta. What I'm going to do is I'm going to do 2 lots of that integral for a, so that was between 0 and pi by 3. Remember, when you're integrating it, it's that all in a bracket squared. So that's my region A there, okay. Plus, I'm again going to use my symmetry, so 2 lots of a half integral, and what I've got here is 5 cos theta squared, and my limits here, I always put a smaller one on the bottom, pi by 3, and the bigger one on the top, and that, oops, that should be a 2. That is my region B that I've done there. Okay, so it's really, really important that you just take a little bit of time to think carefully about what limits you're going to use for which curves, and do it by drawing out from the pole, drawing out these values of theta. Do that, okay, to help you determine which ones you're going to use. Okay, now really it is just plugging through with working these out. So I'm going to double bracket out this, so I get cos squared theta plus, careful, we get 4 cos theta, and then plus 4. Okay, I can't combine these, remember, because they have got a different limit. So that's pi by 3 and pi by 2. Okay, and that one I've got 25 cos squared theta. So here's where I use my double angle formulae. Okay, I haven't got a lot of room here, so I'm going to pop it up here. Remember my double angle formulae, cos 2a, 2 cos squared a minus 1. So when I rearrange it, I get cos squared a equals cos 2a minus 1, sorry, plus 1 over 2. Okay, so that is my double angle formula that I'm going to use. Okay, so let's pop that in here. I've not integrated yet, so I'm just going to pop in for the cos squared theta. I'm going to pop as cos 2 theta over 2. Now I have got an extra plus a half, but I'm going to combine that with my 4. So I'm going to write 4 cos theta, and that's 4 plus a half, which gives me 9 over 2. Okay, and then this one, again, I've got my same limits, lots of writing, but lots of marks, okay. 25 times cos squared theta gives me 25 cos 2 theta over 2, plus, do you remember the 25 over 2? Easy to forget that because it's 25 times all of it. Right, let's now do my integration. Remember, cos goes to sine, but because we've got a 2 theta, we do a divide by 2, so that becomes over 4. Again, with this one, cos goes to sine, and my 9 over 2 becomes 9 theta over 2. Okay, pop my limits next to my square box. Do write carefully with things like this. It's very easy to transpose a limit wrong or to write the wrong number down. So your working needs to be really nice and clear, okay? Cos 2 theta integrates to sine 2 theta. Remember, we get the extra divide by 2. And my 25 over 2 becomes 25 theta over 2 between pi by 2 and pi by 3. Okay, we're ready to pop our limits in, so let's pop our limits in. We've got sine 2 pi by 3 over 4 plus 4 sine pi by 3 plus 9 pi by 6. bottom limit, that's quite nice, -0, otherwise I don't think I'd actually have enough room to put it all in there. So that is my first integral. Two limits to pop in for this, so 25 sine pi over 4 plus 25 pi over 4 minus 25 sine 2 pi over 3, remember the over 4, remember this is minus as well, 25 pi over 6. So pop your limits in carefully. Okay, I'm just going to do a little bit more evaluating here, because if you put all of that in your calculator, it's likely to give you a decimal. Okay, so let's work each of these out individually. Sine of 2 pi over 3 is √3 over 2, so I get √3 over 8. Sine pi over 3 is √3 over 2, so I get 4 √3 over 2. So that one I'll just leave like that. Okay, sine of pi is 0, so that bit goes. I get 25 pi over 4. Okay, so this bit's 0. Sine of 2 pi over 3 again is √3 over 2, so I get minus 25 √3 over 2, so that makes that over 8. And I've got this one. So the question did ask for you for an exact value. So what I'm going to do now is I'm going to combine together all of the bits with pi in. So that's that bit, and that bit. And I'm going to put them in my calculator. Okay, so I don't have to worry about fractions. Pop that in your calculator and you get 43 pi over 12. Then I'm going to combine together all of the bits with the √3 in. Again, put them in your calculator. So what have we got? The √3, we've got this bit, we've got this bit, and we've got this one here. So put those in your calculator, and we end up with just minus 1 √3 there. Okay, so that, it says exact area, so that is how they would want you to leave it. So do make sure when you're working through these, do a bit at a time. And if you put it in all in your calculator and it gives you a decimal, you're going to have to break it down a little bit more to get your exact answer. Okay, that's a lot of working. That shows you've got to write really nice and clearly and be really nice and accurate with these. Okay. Right, we've just got one example. Okay, so they've asked you to sketch two polar curves. Okay, they've asked you to sketch r equals 2 cos 2 theta. Okay, and then they've asked you to also sketch, they've called it a curve with polar equation theta equals pi by 12. Well, hopefully you realised with that, that's actually just going to be a half line out from the origin. Now let's do a little bit of work to see what this one looks like. You should now know with things like cos 2 theta, you get your two petals. Let's see where they are. Okay, so tangents to the pole. That's when r is 0. So we're going to have cos 2 theta equals 0. Okay, so 2 theta equals plus or minus pi by 2. So theta equals plus or minus pi by 4, which is actually what the range of values they asked us to draw. So I'm just going to do it up here because I haven't got a lot of room to do the second part of the question. You do it a little bit more space. Now it does say just draw that between pi by 4 and minus pi by 4. Okay, so I'm going to dash in my tangent to the pole there, and I'm going to also dash in my tangent to the pole here, and I'm going to mark what they are. So we know, again, when theta is 0, we know that r is going to be 2. So it's going to give us this petal that comes out like that. Ooh, that's a little bit bad, so it should be a little bit better than that, and that should come out. Let's make it. Ooh, that's a little bit right. I'm just going to try and rub that a little bit out. Sorry, that just didn't go very well there, that bit. So let's try again with that. Okay, so I'm going to draw it a little bit more symmetrical, seeing as there are some marks for this, and it goes out to 2 there. Okay, the other thing we need to draw on then, okay, I'll do it in a different colour. Theta is pi by 12. That's going to be a straight line that comes out here, something like that, and label it theta equals pi by 12. Okay. Now it says, so that's fine for your 3 marks there. It says for part B, it says find the area of the smaller region bounded by those curves. So if I have a look at my diagram, the smaller area they're looking for is going to be this shaded area here. Okay, so what's quite nice with our diagram, we can immediately see that what we're going to want to do is we're going to want to use that curve r equals 2 cos 2 theta. Okay. But this next bit points something out really nice and clearly to you. Okay, yes, we know our formula for our area, which we always say is half r squared d theta. Now, when I'm integrating to find that part, I must make sure that I use the tangent to the pole as my upper limit. Okay. And I don't go and use, say, pi by 2. All right. Reason being, if I was to draw all of that curve, then don't draw this on. If I was to draw all of that curve, I would have a bit over this here with another tangent to the pole like that. Okay. There is no curve drawn here, but the only reason there's no curve drawn there is because the r equals 2 cos 2 theta is negative there. Remember, we don't draw the negative values of r. There is actually, though, part of a curve here, which is, if I dash it in, don't draw it on yours though, this part of the curve, okay, would be drawn from this part here. If we were to draw negative values of r, we draw it out the other side. You'll see in some textbooks and some examples on the internet, sometimes people do draw the negative values of r. What you'll find is if you use the limits pi by 2 up, pi by 12 up to pi by 2, you'll get some of this curve as well, so you get a different answer. Okay, so do be careful to make sure you use tangents to the pole rather than just where you think the curve stops. That's why I wanted to do this example for you. Okay, so now we can just plod on with it really. Lower limit pi by 12, upper limit pi by 4. What's my r squared? Remember to square that and to square that. Double angle formulae again. Okay, cos 2a, 2 cos squared a minus 1. So then rearrange it. 2 cos squared a equals cos 2a plus 1. And we see actually, when we cancel the 4.5, we do get 2 cos squared 2 theta. Okay, so to be careful with that, this is my 2 theta. So this must be my 4 theta. Okay, so what I end up with is cos 4 theta plus 1. Look carefully to see what that angle becomes. Okay, and you use your double angle formulae. Okay, do our oh, we've not, dear, right, let's rub that bit out. Okay, easy thing to do this. All I've done at the moment is I have replaced my things in my integral. I have not integrated yet. Okay, I'm getting ahead of myself. So I'm replacing that with my cos 4 theta plus 1 d theta. Okay, now I'm integrating square brackets. Sine 4 theta, argument stays the same, and remember you get the divide by 4 and then a plus theta. Okay, pop in your limits. So what do I get? I get sine of pi over 4 plus pi minus sine of 4 pi over 12, which is pi by 3. Remember the over 4. Remember it's a minus as well, minus pi by 12. Okay, that should be a pi by 4 there, shouldn't it? Because it's a theta. Okay, so evaluate these bits. Assign pi goes to 0. I can collect together the pi by 4 minus pi by 12, which use your calculator gives you pi by 6. Sine pi over 3, root 3 over 2, so I get root 3 over 8. And I'd leave my answer like that. Okay, so for that question, that's the important bit that's come up from that extra example, is the fact you must use the tangents to the pole that bound the loops of the curve as your upper limit, rather than necessarily looking at the vertical axis or the horizontal axis. Okay, lovely. Right, so over to you then. You've got 3 questions to do. Doesn't sound like a lot, okay, but they are quite in-depth questions, so I want you to do a really, really good job on those with really nice clear working all shown. Okay, check your answers in the back. Majority of them ask for exact values of things. Okay, oh, some of actually 7 says to 3 significant figures, all right, but keep exact values for things. Think about your limits carefully and show all of your working. So you're going to get those done. I'll set up the assignment on Teams for you and get them submitted by Friday, please. Okay, thank you very much.